So we've been talking about collision avoidance as one of our example problems, and many of you know both Mykel and I worked on a system called ACAS-X, which does airborne collision avoidance. And what's really cool about this is, I mentioned, I think at one point in this class, they trained this model of the airspace on 9 months of radar data across the continental United States. For those of you who took AA228, this model is actually represented as a Bayesian network, which is pretty cool. And you can basically sample aircraft encounters from this Bayesian network in order to simulate two aircraft flying at each other to understand whether or not your system will be preventing a near mid-air collision, or an NMAC. And so what you want to end up computing is the probability that with your system, the aircraft result in a near mid-air collision, given that they're in some sort of encounter scenario. And so you could do that by just sampling a bunch of encounters from this Bayesian network and then trying to see how many of them result in NMAX when you use your collision avoidance system. But as they mentioned in the paper, and as we've kind of talked about quite a bit in this class, is that this approach tends to be quite inefficient because you're not going to get very many near mid-air collisions, because in the airspace it's generally pretty safe already. Like you're not in a lot of scenarios where you would result in a near mid-air collision, which is a good thing. And so if you want to get kind of a better estimate on these things, you can actually sample from a different distribution by kind of biasing the distribution after you sample from the Bayesian network to have smaller vertical and horizontal misdistances. And then that will give you the more interesting behavior you need, and then you can do this kind of importance reweighting in order to get an estimate of the probability of near mid-air collision. So there's kind of just a cool real-world example of importance sampling helping out in basically estimating the probability of collision for the ACAS-X collision avoidance system. So yeah, if you guys are interested in more, I'll share this paper on ED. It was written by Mykel, so it's of course a wonderful paper, and you can check it out.
You see the use of /mid there.
They use a /mid. Although I'm not so sure about this italicized, I don't know, but this was years ago, so. You've grown since then, one of you.
Growth mindset.
Growth mindset. Okay, cool. So with that, we're going to talk about explainability today. And so so far in this class, we've actually kind of just been like this. So we've either been it doesn't work or it does work. We found failures, we estimated the probability of failure, we sometimes proved that there were no failures, and sometimes that kind of gave us insights into what was going on, but we're never really explicitly explaining why does it work, why does it not work. We're just kind of it works, and sometimes that's okay. Sometimes you can just be all right, it works, we have a proof that it works, so I'm good, I'm just gonna go for it. But sometimes it really does matter why it actually works or why it's doing what it's doing, because you could get fooled by it. It could always be working and all of these things that you're validating over, but maybe there's some metrics that you kind of missed out on, and it turns out it would do really poorly on those metrics. And if you can instead kind of explain the behavior of a system and be okay, the system is making this decision or it fails in this way because of this, this, and this, then you might have a better idea of what's actually going on, and you can feel more confident when you deploy the system in the real world. So sometimes it's good to know why it actually works. So that's what we're going to do today. We're going to talk about a whole bunch of different techniques for explainability. We'll start with policy visualization. Then we'll talk for a while about feature importance. We'll talk about surrogate models for explaining policies. And then we're going to talk about the last two topics kind of briefly, but we'll talk about counterfactuals and failure mode characterization. So let's just jump in here. Policy visualization, we've actually already done a whole bunch in this class. Because really what you could do is you could just visualize some rollouts of your system. So we've done this lots of times. So for example, we could roll out our collision avoidance system a whole bunch of times and just look at what happens. And so we can see there's kind of two modes of behavior. It either goes above the intruder or below the intruder. And really, this is kind of one of maybe the first things that you would do when you design a system. You just roll it out and make sure it looks reasonable. Same with the inverted pendulum. We can see, for the most part, it just kind of stays upright with an angle of 0, and then sometimes it falls over. Okay, so that's one thing you could do. Another thing you could do is try to plot the policy of the agent. So let's actually look at the one on the right first. This is the inverted pendulum policy. And what's nice about the inverted pendulum is it has a 2D state, and the policy is only dependent on the current state. So we can look at what the agent would say to do if it was given an observation of any of these states. So we have theta on this axis, omega on this axis, and we can just sanity check that all of this kind of makes sense. So for example, at 0, 0, so that means we're perfectly upright and we're not moving at all. We would hope then that we would just stay that way, so we'd want to apply a torque of 0. So we can see here, we get a torque of 0, seems reasonable. If we move to the right here, where theta is positive, we get a negative torque because we want to push it back up the other way. If we move to the left, we get a positive torque to push it back up, and so on. So this is kind of just a nice sanity check to plot the policy. For the collision avoidance system, we can do a similar thing, but now the actions are discrete. So here we're plotting a slice of the state space where on this axis we have the time to collision, and then on this axis we have the relative altitude between the own ship and intruder. So you could imagine like the own ship is right here, or sorry, the intruder is right here in the plot. And then you could imagine if you kind of put the own ship at any of these places, this is the action that it would get. So if we're like above the intruder, we get told to climb. If we're below, we get told to descend. And if we're far enough above or far enough below, we get no advisory, clear of conflict. We don't need to do anything because we're not in like a dangerous situation. So this is very interesting, and this is actually something they did when they were first generating the policies for ACAS-X. And you can find some kind of interesting unintuitive features. So for example, kind of like this notch back here. Does anyone, maybe if you've taken AA228, does anyone have any ideas of why this notch isn't like filled in, why it's no advisory? Yeah. Yeah, so we don't know if it's gonna like, whether or not climbing or descending is gonna be better yet. So it's kind of interesting. You can like discover interesting features by doing this policy visualization. So it's definitely something that I would recommend as you're designing systems. And then another thing to note here for the collision avoidance policy is specifically that we're plotting a policy slice. So what's nice about the inverted pendulum is the state was only 2-dimensional. So we could just plot the entire policy and see what it looked like. The state for the collision avoidance policy is actually 4-dimensional. So we can't just plot the whole thing at once and visualize it. We have to plot slices because, again, we don't really know how to visualize 4 dimensions. And so you have to plot different slices of it. And so another kind of way to do this when you have these kind of more complicated high-dimensional policies is to partition the state space. And I know this is blurry, it's really bothering me, but I honestly didn't have time to fix it, so I'm sorry. It's not blurry in the book. I don't know, some PDF renders make this blurry, I don't know what's going on. But anyway, so pretend it's not blurry. So we can also partition the state space into a bunch of regions, and then simulate a bunch of trajectories. So we'll just imagine like all those rollouts that we had from before. And then every time it passes through a region, we mark down what action it took in that region. And so it might not always have the same like vertical rate or previous action within these regions, so it might not always take the same action in each region, but we just keep track in each region of the action that it took. And then, for example, we could maybe plot the action that was taken most frequently in each region. Yeah.
Sorry, what is this trying to solve?
We're just trying to be able to visualize the policy that's 4-dimensional.
And what is like IE versus this versus just rolling out a bunch?
Well, we're plotting the action that got taken as we were doing the rollouts.
Oh, okay, I see.
Yeah, so we're trying to visualize.
And unlike the pendulum, it's like history dependent. That's why.
On the pendulum, it's not history dependent.
Unlike the pendulum.
Oh,
history dependent.
Yes. Actually, this one's not history dependent. It's just because we're plotting a slice of the state space that you might get different ones. But that does bring me to my next point, which is what's really nice about this method is it works for non-Markovian systems. So if it is history dependent, we can't just like look over the state space and be like, in this state, I'm going to take this action, because it also depends on how you got to that state sometimes. And so in this case, we can actually just simulate a bunch of rollouts, then we know how we got to every single state, and we can still make this kind of visualization. So this is nice if you have like a complex, potentially non-Markovian system as well. Okay, great. So that's the first thing. So just visualize your policy. That's something that's always pretty simple to do, but also can be quite useful in finding bugs. Okay, so now we're going to talk for a while about this thing called feature importance. I think this is what a lot of people think of when they think of explainability. And basically, the goal of feature importance is to understand the contribution of various features to the overall behavior of a system. And features could be lots of different things. So it could be like the state of the system, it could be the disturbances that we apply, it could be like the pixels of an image, lots of different things. We want to understand how those things influence the behavior of our system or some output that we care about. So here's like a couple examples to make it more concrete. So say we have like an aircraft that's taking images of a runway, and we're using those images to steer ourselves down the runway. Then we might want to know, given a particular image, what pixels in the image were most important for us to decide on the steering angle that we were eventually going to take. And so the brighter pixels in this image, I'll talk about how we like find this in a second, but this would give us an idea of the pixels that were most important in deciding what steering angle to take. And then similarly, we can do something with trajectories for disturbances, where we would say, so here's our inverted pendulum trajectory. Each of these dots here is like an observation disturbance, so it's like where the pendulum thought that it was. And then the darker dots indicate points that, or disturbances that were more influential in the final outcome of the trajectory, or in the robustness of the trajectory. And so it turns out that disturbances earlier on, and we'll see this in a second, end up being more influential than disturbances later in the trajectory. Cool, so there's kind of two ways that we can think about feature importance. One way is something called sensitivity analysis, and the second way is Shapley values, and we're going to talk about both of these. So starting with sensitivity analysis. So what sensitivity analysis allows us to do is to understand how a particular output changes when a single feature is changed. So here's an example here, just kind of a notional example. So let's imagine we have like a trajectory of an agent through some environment, and the white trajectory is like the trajectory that we see. And so these both have the same like white trajectory here. But then let's say that we change one feature, so we maybe like resample a disturbance at this point in the trajectory, and then we roll out the rest of the trajectory with the same disturbances from there. So we just perturb kind of like one point in the trajectory, and we do that for both of these. Can anyone guess which of these has a higher sensitivity? The one on the right or the one on the left? Yeah, okay. The one on the right. I think you're all pointing the opposite way for me, but yeah. Okay, this one has higher sensitivity. So basically all we're doing is trying to understand, like, if we change this thing, does it affect the final outcome a lot? And if it affects it a lot, or we have this kind of high variability of possible outcomes, we say it has high sensitivity, and if we have a low variability of possible outcomes, it has a low sensitivity. Okay, so here's one way that we can compute this. So let's say that we wanted to compute the sensitivity for all of the disturbances in a particular trajectory. What we could do is that, say we want to compute the sensitivity of kind of the final result of this trajectory, or maybe the robustness of this trajectory, with respect to just this first disturbance. So what we could do is we could say, I'm going to keep all the disturbances the same for the rest of the trajectory, but I'm going to resample this first disturbance, maybe from like its nominal disturbance distribution or something like that. And then we're going to simulate all those resampled versions and see kind of the spread of the trajectories that results. So we could maybe look at like the spread, or for example, the standard deviation of the robustness values we get when we resample and simulate those new trajectories for that point. So that's how we get this, and that gives us the sensitivity of this point. We could do that again with the next disturbance, so we're going to keep this disturbance constant and all the future ones constant, and look at the spread over trajectories. And then we can just kind of repeat this for the rest of the trajectory, looking at the spread of the possible resulting trajectories when we change that disturbance. And maybe I'll just play that one more time. You'll notice that as we kind of get towards the end of the trajectory, the spread decreases more and more. And so you can see that we end up finding out that the robustness is less sensitive to the disturbances applied later in the trajectory than the ones applied here.
Isn't this always true with any multiplicative system? Like, because variance, say a V-shape is the random variables and multiply them all together, then the variance which is monotonic values.
I feel like if you had like a really bad disturbance right here or something, you might find that it's really sensitive to the disturbance
in general,
there.
say the disturbance was roughly similar across everybody. Doesn't earlier point always, like moving earlier points always get
I think that's generally true. Yeah. I'm not saying we necessarily found an interesting explanation, but we found an explanation. Yeah. So I think, but it's a good point. It's kind of like these things come out and it's up to humans to like interpret them and decide if they make sense. So maybe you do interpret this and you're like, yeah, makes sense. Like earlier ones should affect it more. And then you just kind of go with that.
Or we always blame our childhood.
That was a good one. Okay.
So when you say spread, does that mean variance?
That's one way to calculate spread, yeah. So when I made these colors, that is what I was looking at was variance. You can pick any metric you want to quantify spread. Okay, so we can also do this for our taxi problem. So just to define it a little bit more, we have this image of a runway, and then what we're going to do is we're going to pass this image of a runway through a neural network, and it outputs a steering angle that's supposed to kind of keep us going straight down the runway. And this is 64 by 64, so it has 4096 pixels total. And so what we could do is we could go through each one of these pixels in here, keep everything else the same, resample just the value of that pixel, and see how it changes our steering angle. And then we can plot the relative change of all of these steering angles, or the relative spread in the change of the steering angle on top of the image. So when we do that, we get something like this. And so it's kind of noisy, but it looks roughly like the most sensitive pixels are the ones that are kind of in the portion of the image which would really help us localize where we are, because it's the portion of the image that kind of shows the edge lines and some of the center lines. So we can look at this and be like, okay, it kind of seems like it's paying attention to the thing that we expect it to. Any questions on that?
To actually get this, I mean, you're not perturbing each pixel, are you?
I am, and what might be the drawback of that?
Backdrop.
You could, yeah. Yeah. Why would we want to do that instead of this?
I like a little faster.
Yeah, it goes a little faster. Yeah, so exactly. This is like pretty inefficient. So this is kind of like what we're going for. We want to find like if we change this, what happens, but doing that sampling for all 4096 pixels actually takes quite a long time, to the point where when we were putting this figure in the book, I actually cached it so that it doesn't redo this every time the book compiles. So it is quite expensive. And so we could reduce the computational costs using backpropagation or using something called saliency maps. And the idea behind saliency maps is that they use gradients to identify inputs that are most important, or salient, that's where the word comes from, in determining a particular outcome. So basically all we're doing is we're, in this case, going to take like the gradient of the robustness of the trajectory with respect to each disturbance. And the idea is that inputs that, or features that have higher gradients, that means that small changes in them will affect the output more. And so if we just kind of plot the magnitude of the gradient, that should indicate which features it's more sensitive to. That's the general idea. And it turns out that seems to work pretty well. So here's what it looked like when we did the sensitivity analysis, where we perturbed each one at a time, resampling. And if we just take the gradient, we get something that's quite similar. So that's another way to kind of approximate these things. We can also do that with the taxi problem. So here's what we got when we did, perturbing each one individually. And then when we take the gradient, we get something a little bit different, but it's focusing on a similar area, focusing on the edge lines of the runway. Yeah. When is it worth doing both? That's a good question. I think like one point I want to make on this slide, and that I'm going to kind of continue to make on the future slides, is like this produces like a slightly different explanation than this. And it just means they're kind of different definitions of sensitivity. So maybe this one's like a little more local because you're taking the gradient and and that just talks about like a small region around your current input. But in general, I think it can be difficult to interpret, like, why does this one seem like it's focusing here and this one seems like it's only the edge lines? And it's not always obvious. And that's kind of one of the challenges with explanation techniques, because it's kind of up to the human then to interpret whether they make sense. So sometimes it might make sense to do like a few of these methods and see if they all produce something similar, but yeah. Okay. Cool. And so there is still one issue with this method though, or maybe a few issues with this method, but one of the issues is that it might miss out on saturated features. So here's what that means. So let's look at a really simple example. So we just have one input feature and we're interested in the output f of x. So our input feature is x and our output is f of x. So just looking at this plot here, does it seem like f of x is sensitive to the value for x, would you say? Yeah, nodding your heads. So yeah, I would agree. I think it's sensitive. Like as we change the value for x, f of x is definitely changing here. But let's say that we were looking at one individual data point, and our current point was right here, and we used the gradient to help us understand sensitivity. So then we would get a gradient that looks like this. And it's pretty flat. So we're going to kind of conclude that f of x is actually not really sensitive to x because this gradient is very flat, it's very small. But that's not necessarily what's going on here. It's just that x is in kind of a very saturated point of the feature function, basically. And so what some people do instead is they say, let's start at some baseline point. So maybe we start at 0. And then let's take the gradient there. So now we've got a much bigger gradient. And then we can kind of just make our way, continually taking gradients to the current point that we're at. And so now you can see, as we take, and then basically what we do is we average over all of these gradients here. And so we'll get some non-zero or not super flat gradients in there to show that this output is actually sensitive to this input. So this algorithm specifically is called integrated gradients. And basically you just start from some baseline, gradually move to the current point that you're at, and then average the gradients along the way.
So I guess if you want to see sensitivity to nominal things, like you may have saturation for some features in nominal situations, but you may have, if I can compose any image, then this neural network will have remarkable amounts of gradient for specific pixels. So maybe is it like if I were to push all of the data set through and then zero out the loss and then backprop through it or whatever procedure you have, and then average all the saliency maps versus starting in a baseline. I don't know what the baseline is, but let's say it's the zero image.
Yeah.
Which is not, hopefully wouldn't be the case with blindfolded plane. But that's added distribution.
Yeah, I think the idea, so I'm actually going to show an example next where we do start with the baseline of the 0 image. That seems to be the common thing that people who use this method do. I think the idea is like if you start from a completely black image, and we're going to see this in a second, and you kind of make your way to the, so you like slowly basically increase the brightness until you get to the image that you're interested in, features will kind of appear at some point. Like at some point you'll like really be able to see the edges and whatever. And then you want to capture basically that moment when it appears and get like the gradient. That's kind of the idea.
And when you're doing this, your current point is one example image?
Is one example image, yeah. So you would need to pick a handful that you think. Yeah. Yeah. Yep, good question. Okay, so yeah, let's see that example. So we're going to do the same texty image that we saw before, but right now it's completely black, so we don't actually see any of the edges. And so I'm going to play an animation in a second. And what I want you to do is pay attention. So we're going to look at the gradients as we kind of move from this black image. It's slowly going to increase the brightness to the image that we're interested in. And as we move from this image to that image, we'll look at what the gradients for this pixel right here that's kind of highlighted in blue look like, and then the gradients for this pixel that's highlighted in green look like. And it's going to be plotted over on this axis here. So let's just watch this here. Okay, so that's kind of what happens. Maybe I'll try to play it one more time. Oh, that didn't work. Oh no, hold on. What's happening? There we go. Okay, play that one more time. Okay, so basically what happened here is like, as we might expect, this green pixel here, it's not really near any of the edge lines. It doesn't seem like we should be sensitive to that. And in fact, we find that the gradient is pretty small the whole way there. Whereas this blue pixel here, we have kind of this big change in gradient as we move from the black image to our true image, yeah.
So are you plotting gradient or the function? So
I'm plotting the gradient.
the gradient. So blue is not only large in terms of integrated gradients, it's also like large and just gradients are keeping high the whole time.
Yeah, that's true. I kind of wish I found an example where that wasn't the case. But yeah, this would also have ended up working fine with the saliency map. Any other questions on this?
So this is what we call explainability, right?
Yeah.
So now let's say we have done this, and we do explainability actually usually to solve a bigger problem, right? To like, I don't know, try to reason how this model can use in a greater context. Can you maybe explain, if I do, for example, this, how I can use this to solve, like, what is then explainability useful for, I guess?
I think what explainability is useful for, so I'm actually going to very shortly provide a word of caution about using all of these things, but in my opinion, if the explanations are true to what's going on, what's useful for having explainability is like, your system could be like fooling you that it's correct, right? Like you always want to still like scrutinize good results too, because you might have some bug that like actually caused you to get the good results. So we could do all of these other validation things, be like, oh, the probability of failure is really low, or like we proved that under these assumptions it works, but maybe it's working for like all the wrong reasons, and then it's not going to generalize correctly. And so in my opinion, what explainability would do is give you some extra confidence to be like, no, it's focusing on the right thing. It's focusing on the feature that we think it should be focusing on to make this decision. That's how I would say it to you. Yeah. It might also help you understand where you might find, like where you might have additional failure modes of your system.
Use very big words like proof and generalization related to this.
Well, yeah, I think like if you find that it's focusing on these lines, I might expect it to generalize to another image where there's lines.
I mean, that we don't have to go into this, but I think there's a bunch of papers that show that you can get good looking, like you can use methods like this, saliency maps, and it looks kind of good. But actually, this is a very misleading result, and the model doesn't really.
Yep, we're gonna get to that. I agree with you.
We had a whole hour discussion about this.
We did have a discussion about it. It's a bit contentious. Okay. So anyway, but I'm showing you the basics. This is what people do. Okay, and I think, yeah, in general, so you can even get like different explanations of doing this. So I think like integrated gradients, it did in fact kind of smooth out what was going on with the taxi thing. Now it seems very clear that we're like looking at the edge lines of the runway. These are all just different definitions of sensitivity. So we have to decide as like humans what we want to make of it. Yeah, did you have a question?
I'm just a little bit on what baseline input is here. Is that like problem specific?
It's problem specific. For images, people often will use like an entirely black image or an entirely white image. Yeah. But you just kind of have to pick something. Any other questions?
Is it the most useful reason why I've done this in my life is to identify burrito buckets of why your model's failing at test time, and now you have burrito buckets, and then you add more data to prove it on those burrito buckets. And so if you want to know why, if you want to improve it, it's not working. I got 80% F1 score. Cool. What do you do?
Okay, so use it like to identify like why things might be failing or where you might need more data. Kind of?
Yeah, like for example, at Apple, we were, we didn't get into it, but we were confusing parking lots and golf courses because the trajectories are very similar in both. your GPS data is going to look very similar in both situations. And so we're like, oh, or and we can identify that these are the in the world, this is the maps that we're getting really inaccurate on. And what are they? Oh, that's a parking lot and that's a golf course. Okay, we need more data or add RGB because one does not look like the other. So then you can have those conversations.
Yeah.
But I think there what you're actually doing, and I think that this is a great approach for interpretability, but actually you're looking at the samples that you do poorly on, and then you actually consider metadata about it. So you take the set of poor samples, and then you notice, oh, these are actually all golf course images. But now the feature that you're actually interpreting is the fact that it's a golf course, and not whether the pixel is green or gray.
It was a golf course. It's actually saliency on geospatial, on the full globe. So we have a net going in and output, and then output in some class we wanted to track. And then we did this method, and this is the areas that we do the worst on.
Okay.
Versus a big block, right?
Mm-hmm.
Now it's this specific pixel that's really causing a lot of issue. Okay.
Yeah, and I guess like one more use for explainability, if done well, is sometimes you have shareholders that they need an explanation. So like there's like some regulations, like if you're operating in certain domains, they actually require you to be able to explain what your system is doing, whether it's a faithful explanation or not. And so you need to be able to provide these, and ideally they're working correctly. Okay, and there's like a ton of others. So like I just touched on like saliency maps or kind of the vanilla saliency map is this gradient magnitude thing. That's one I touched on. I touched on integrated gradients, but there's like a ton of other versions of these things that people have come up with. Smooth grad is like a popular one where you just take the gradient of a bunch of noisy versions of your image and average that together. There's just like a ton of these. But here we go. You should be careful. So this is my word of warning to you. So this actually comes from a paper that's kind of, specifically this paper called Sanity Checks for Saliency Maps. And they're basically talking about how a lot of these things, you need to be careful the information that you draw from them. And basically the idea here is like, they have this image of a bird and they're providing explanations for why it's calling it a bird. And each of these different explanations, types of explanations, produces kind of a different saliency map. But it all kind of looks like the bird. And then it turns out though, if you just like take the image, like you ignore the model that you're trying to explain completely, you just put the image through an edge detector, you get this image on the right here, which kind of just looks like all the explanations that we saw before. And that's not so good, right? Like we don't want the explanation of the model that we're trying to explain to not depend on the model that we're trying to explain. That's not a good thing. And so what's kind of interesting is they like note in just their abstract here, they say like through extensive experiments, we show that some existing saliency methods are both independent of the model, which is what I just said, and the data generating process. So they also show in this paper that you could just like mix up all the labels of your data, and then you still get the same explanation for like why everything is, which shouldn't feature. Yeah.
But this is not entirely bad, right? In the sense of like this. Sorry, this makes like maybe I'm like too pre-training right now. That's why I'm thinking about this. But like in some sense, like you're learning some feature about the picture that's inherent in the picture. Like if I see a picture of a bird, no matter what I'm trying to do, it's like a bird. And then like whatever the downstream task is, it's like a bird. And
yes.
Learning to learn, like the model learning to look at edges is like a net good thing, no matter what I'm trying to do.
I think you are like in a pre-training brain. I think. So they actually do talk in this paper about how like there are certain architectures that have inductive biases. Yeah. So like, yes, you put a convolutional network, and then like even if you have random weights, like you still might get an edge detector anyway. This gradient?
Yeah. Like,
I don't know if that really looks like anything, but yeah. So that's one thing to be cautious about, and actually like just to build on that. So like this is like very concerning. So this is basically that row that we were just seeing here with all of the different methods with like the original explanation, and then what they did in this paper was they took each row, they went kind of layer by layer in the network and just replaced the weights of each layer with random weights. So here they just replaced like the end layer with random weights, just the logits. And then as you move to the right in this plot, once you get all the way here, you have a completely random network. So it's not the same model at all that you were trying to explain before. And they just kind of look the same as you go all the way across. So this is like very concerning. They showed that some of the methods, this doesn't seem to happen. Like I think this one maybe, I don't really know. But it's just some caution that you should take this into account when you're going to try to apply these methods. I think it's easy for us as humans to like make explanations out of things if we stare at them for long enough, but it's not always a faithful explanation. So in general, we should be careful to ensure that we do not find meaning where there isn't any. I really thought there'd be a good joke here, and I ran out of time, so sorry. We're at that point in the quarter. But did send me a really funny thing right around this moment last night, and so I was like, oh, I'll just throw this in there. Okay, so I've seen things like this before. Like actually one of our lab mates wrote one of these for Julia. But this is honestly, I think, like one of the best ones that I've seen. So I'll just let you like appreciate it for like 10 seconds or so, because there's some really good stuff in here. Is it?
There's an actual rescue.
Does it throw?
Rust exceptions are weird, but it does do something similar to that.
Gotcha. Yeah, this one's just, it's good. So
Yeah,
things are
I
over.
looked at every one and it all makes sense.
Yeah, they're all so
No, even though I'm a millennial, like, I couldn't.
vibe check. Yeah, I'm a big fan. Still
Oh, yeah.
Anyway.
His ratios watches.
Okay.
What have we got?
All right, moving on. You can download the slides later if you're not done looking at it.
One more thing on interpretability, if you want something beyond the grad cam, I think these days there's this topic called mechanistic interpretability, which is kind of hot right now, but it's very much an unsolved problem, but it kind of tries to solve instead of doing interpretability on a pixel level, can we do interpretability on a semantic level? Like, a bird is made up of a beak and a wing and these kind of things. And I think it's an amazing research topic if you're looking for research problems.
But equivalently, it has the same issues of just like, it could be complete nonsense.
Yeah, you can talk to if you want some alternate opinion.
Sorry, we had an hour-long conversation about how I dislike mechanistic interpretability because I think it's actually exacerbating this problem, not minimizing it.
Highly contentious topics today.
Yes.
Okay, but I think all of this is really good to think about, and one thing that gives me hope is like if we can really get to the core of what these models are doing and we can have these like explanations that really do explain what's going on, I think there's a lot you can do about them, but there's research to be done, I think, is where we're at. Okay, so that's sensitivity analysis. And then the other thing about feature importance that I want to talk about is these things called Shapley values. And basically the key difference here is that when we were just doing sensitivity analysis, we were looking at the effect of varying only one feature at a time. Whereas for Shapley values, we're able to actually capture like interactions between features. So let me kind of motivate why we might want to do this or where this might matter. So we're going to consider a super simplified version of a wildfire scenario. So imagine we have like some region of the world and we divided that region into different cells that could either be burning or not burning. So the not burning cells are in white and the burning cells are in red. And let's say that like most of this is land that like is not really occupied, so we're not super concerned about it. But in this upper right corner here, maybe there's like some expensive property or homes or people, and we want to make sure that this is not going to catch on fire, or at least we want to understand the probability that this particular corner catches on fire. So this is our current state. We're going to represent a state as just like which cells are burning and which are not burning. And then we have, we're going to have a very simple version of dynamics for this problem, where the probability that a cell is burning at the next time step is going to be 1 if it was burning at the previous time step, so we'll just assume it's going to stay burning. And then every cell that's neighboring a cell that's burning at the previous time step has a 30% chance that it's burning at the next time step. Okay, so all these probabilities are just zeros here, and then this is like neighboring a cell that was burning, so it's 0.3, and so on. So basically now we can say that in this kind of cell that we care about, we know that the probability that it's burning at the next time step is 0.3. Okay, so now let's look at this cell particularly right here. So say this is the feature that we're interested in. So we'll say each of our features is a cell. We're interested in this feature. Does this cell have an effect on the probability of the upper right corner burning? What do you guys think? Yes, yeah, I would say that it does. But if we're doing sensitivity analysis, here's what would happen. We would just remove this one feature. We would change just this feature. And then if we look at our probability of the cell burning at the next time step with just this one removed, it's still equal to 0.3 because we still had this cell burning, and so this one is giving it this 0.3 probability because we just need one of the neighboring cells to be burning for it to have a 0.3 chance of burning at the next time step. So if we were just doing this like sensitivity analysis where we just consider one feature at a time, we would actually conclude that this cell here has basically no effect on whether on the probability that this cell is burning at the next time step. Yeah.
Actually, wouldn't we conclude that either has an effect on
This one too? This one too?
Yeah.
Yeah, we also conclude that. That's correct. Yeah. So basically what's going on here is we're like missing out on the interactions between these features because it does still matter. Like we need at least one of these two to be burning. And so it does seem like it still affects it. And so yeah, if we like get rid of this one as well, then we see that it will actually change the probability that it's burning at the next time step because now it has no chance. And so what in general, like what we want to do is actually consider the effect of changing subsets of features, not just changing one feature at a time. And so to do this, we use something called Shapley values. And here's basically the idea. So we're going to go back to our wildfire scenario, and we'll just go back to the state that we were in. Again, we're concerned about the probability of this cell burning at the next time step. And then what we're going to do is we're going to say we're interested in the Shapley value for this particular feature. So we don't want to get 0. We're hoping that we can actually show that it is in fact sensitive to this feature. And then we're going to fix just some random subset of cells. So I just picked like a random subset. All of these blue cells are fixed. We're going to say like they always keep the same value. So if they're burning, they'll always be burning. If they're not burning, they'll always not be burning. And then what we're going to do is all of the rest of the cells, so the ones that are not blue, we're going to randomly sample whether they're burning or not, given like the probabilities of those things occurring. So then let's say we randomly resampled all the ones that weren't fixed, and now actually both of these turned to not burning, they got resampled. And now we look at this probability over here and we see that the probability that it's burning is 0. Then we're going to repeat this exact same process, except we're going to fix this cell to what its original feature value was. So we're going to fix cell I, we're going to add that to the subset of cells that's fixed. So it's back to burning, and now we have this 0.3 probability. And then we're going to look at the difference between these two scenarios. So basically what we're saying is we have this subset where this value was fixed to what its original value was, and then we have this subset where we let this value be randomly sampled. And we're going to look at the difference in the feature value that we care about for when it was fixed versus when it was not fixed. So what we did was we basically said, okay, we're going to fix the subset, we're going to resample all of the rest, and one of the times when we fix the subset, we're going to include the feature we care about, and one of the times we're not going to include the feature that we care about. And that will give us, if we kind of take the difference between these two things, that will give us an idea of how much of a difference including versus not including that feature makes, basically. Yeah.
How do you choose the rest of the blue boxes?
How do I choose like which ones are blue?
Yeah.
Randomly pick a subset.
So we randomly fix a subset,
Mhm.
and then in addition, we then freeze and unfreeze a certain feature, and then once we unfreeze it, we also randomly sample that one as well.
Yep. We freeze and unfreeze the feature that we're interested in computing the Shapley value of.
But what if we happen to randomly pick the other one, like the one that was causing it, the one that like the one in like.
What if we picked this one?
Yeah.
Then we would also get 0.3 we would also get 0.3 here, and this would be 0. But you want to do it, we imagine doing this like 30 times and averaging the result.
Okay, great.
Okay, and so basically what we're doing for Shapley values, it can be a little bit difficult to wrap your head around, but basically what we're doing is we say we want to take the expectation of this difference, so including versus not including, across all possible subsets. So here we did this subset, imagine we like ran it 30 times, computed this difference all those 30 times, got some value, and then we want to just take all possible subsets and do this same thing. Can anyone think of like what might be a problem here? Yeah.
There's like way too many different like substates to check.
Yeah, there's like a ton of subsets. So the challenge is that there's quite a few of them, and in this example where we just have 25 features even, there's over 16 million possible subsets. So for every feature we want to compute the Shapley value of, we would have to try all 16 million subsets, do that randomly sampling a bunch of times to estimate the expectation, and so on, and this just basically becomes intractable. And in practice then, what people do is they'll just like randomly sample a few different subsets, and it actually tends to provide a pretty reasonable estimate. So you can just implement this by randomly sampling some of the subsets, and you don't need to go through all 16 million of them. Any questions on that? Yeah.
Each of the 16 million subsets, you would then need to perform the sampling where you like hold some fixed, and so it'd be actually like k times 16 million. Is that?
Yep. Yeah, exactly. I mean, technically it's defined in terms of the expectation, but that's another thing you have to estimate. So then, yeah, you're basically estimating that expectation. Okay, so yeah, and then I just want you to get in your mind that like all that's going on, it's like kind of a lot, and I didn't show the math purposefully because I think that's even like more confusing to parse, but basically we're just like looking at all possible subsets, seeing how including a feature versus not including a feature in that subset affects it, and then that gives us an idea of how important that feature is in the context of all of the other features that we have. So here's like what the Shapley values for our inverted pendulum look like. And you can see the Shapley values are like the highest for some of these disturbances that make it seem like it's as like closer to upright than it actually is, which makes sense. So if we like if we make the pendulum think that it's closer to upright, it won't apply enough torque to actually move it towards upright, and so these should be the things that like really have an effect on the final outcome of the trajectory. And we can kind of verify this, so what we could do is we could say like, what happens if we remove, let's say like the feature with the 4th highest Shapley value? So we just take that disturbance and we set it to 0. Then we can see that the new trajectory, it changes a little bit. It's like a little less close to failing, but it's still failing. Then we can say, let's take the one with the 2nd highest Shapley value, also changes a little bit, the 3rd highest and the 4th highest. But then if we take away all 4 of these features at the same time, so we zero out all 4 of these disturbances, we get a pretty huge difference in the trajectory. And so we're basically finding out like, what are the 4 features? If we wanted to remove 4 features, or like control our disturbances at these 4 time steps, the trajectory would be not a failure anymore. So that's kind of what the Shapley values can give you. Yeah.
So to get to these 4, would you take top k of the Shapley values?
Yeah, that's what I did. Yeah. Yep. Yeah.
Or is it to see like the interaction of features for like an entire like final trajectory kind of thing, rather than like, because I guess like in the previous example where we had the wildfire base, I thought it was like each subset interacting with one another rather than like the actual output of what. So maybe I'm just not kind of
yeah, so I think what's kind of cool about all these explainability methods is they're like very broad. You want to just know like what is the effect on some output given some set of input features. So in the wildfire case, the output was like whether or not that top right cell was burning, and the input features were whether or not all of the other cells were burning, basically. In this case, the output is the robustness of the trajectory, and the input is the disturbance at each time step. So like, in one case like the features were at a single snapshot in time, and in this case they're like over time. Does that make sense? Any other questions on this?
Thing on staying towards P nominal. Like, it's not all subsets that you're, in this example, like, are you, when you're turning one disturbance on or off, but the process would be, I create a random assignment of disturbances. I do it, and I have this one disturbance be on, one disturbance be off. I get two values, I subtract it. And then I do it again for another assignment. And another assignment, another assignment.
Yeah, well,
But
so you
those
have,
assignments could be completely not possible or rare. You'd want it to be somewhat nominal, right?
yeah, so you would basically, you take the trajectory you had, so say you have a failure trajectory, you're like, I want to understand the contribution of each disturbance to causing this failure, basically. Then you would say, I'm gonna, every time you like compute that difference, you're gonna sample a random subset, so basically a random subset of time steps. You're gonna say, I'm gonna fix the disturbances at those time steps. I'm gonna change the disturbances at all of the other time steps, see what the robustness is. Then I'm going to include the feature that I care about in the set that's fixed, and then I'm gonna take that difference. And then the next time you're gonna sample another random subset, and you're just gonna keep doing this. Does that make sense?
Yeah, I guess like it's the random part is what's concerning to me.
You would resample from probably the nominal disturbance distribution.
Right. That's what I'm trying to get.
Yeah, you would
That's
resample
what I'm
from the nominal distribution because you're taking the expectation over the things that you didn't fix, and the expectation would be with respect to the nominal distribution. Okay, and so yeah, I didn't really go through the math here. I think the notation gets really messy, so we tried as hard as we could in the book to make it as not messy as possible. And we also have it implemented in code if you guys want to check it out. But yeah, so you can go through the math. Like I said, the notation gets messy, but it's like not super crazy what's going on. It's just like including versus not including a feature, and that turns out to be really hard to write down cleanly in math. Okay, so that's feature importance. So that's a big part of what people think about with explainability. Another thing that you can do for explainability is use surrogate models. So we often use these to explain the policies of agents. And specifically, if we have an agent, for example, with a complex policy, maybe a neural network, something like that, we could build a surrogate model to actually approximate that policy. And ideally, we use a surrogate model that's just already easier to interpret kind of off the bat. And so as we're thinking about what to use for a surrogate model, there's a couple things that we might want to keep in mind. One is that we want our surrogate model to have high fidelity, so it should accurately represent the policy that it's modeling, because if it doesn't, then trying to explain that policy is not going to make a lot of sense because it doesn't actually match the policy we're trying to explain. And then second, we do want it to be interpretable, because we want to be able to then take this and look at it ourselves and try to draw conclusions about what the agent is doing. And typically, as you might imagine, there's a trade-off between these two properties, because if we could have a policy with high interpretability that perfectly approximates the true policy, we might as well just use the policy with high interpretability as our actual policy. So in general, there tends to be a trade-off between these two things. Okay, so there's a couple of different examples of models we could use for this. One example is a linear model. So say we just want to model some behavior of an agent represented by this function f of x, then we can just take a linear sum of all of the of weights multiplied by all of the different subcomponents of x. And the reason that this tends to be interpretable is because these weights then provide an indication of the relative importance of each feature. Because if the weight has a higher magnitude, then it's going to have a bigger effect on the output f of x. Okay, and oftentimes we use a local linear model, so a lot of times we're not trying to explain the entire policy of the agent over its full input domain, because linear models typically work best when they're just in kind of some local region. And some of you may have heard this very famous explanation technique called LIME. That's basically creating, it doesn't necessarily need to be linear models, but a big portion of the LIME paper is talking about local linear models of the features. Okay, so just to see what that looks like, this is our collision avoidance policy, a little bit zoomed in. And let's say that we want to create a local model of the policy in this particular region here. So we're just looking at everything that's in this circle what is, or how can we explain like what the policy is doing here? So what we could do is we could draw a bunch of samples from this small region, small circular region, and label them with the action that gets taken at each of those points, and then train a linear model to approximate the policy in that region. So then we end up with maybe something that looks like this. And so you can see within this circle, it approximates it quite well. But again, this is a local model, so if we look at the rest of the policy, it certainly doesn't do a good job approximating it. But we can understand, like, within this region, this model kind of accurately matches the true policy. And then we can actually look at the weights of the model, like we said we were going to, and understand how important each feature is. For example, we can see that it kind of seems like the weight for both the relative altitude of the aircraft and the time to collision is important for determining the action that we take in this particular region. You could probably figure that out without this for this particular example, but in general, when we have these higher dimensional things, building these linear models can be really useful. And then, for example, we could compare that to a local model for a different part of the state space. So for example, maybe we fit a model to this region here that's kind of in the middle. And here we find that we get a nice linear model that separates these two actions. And then if we look at the weights, we see, as we kind of expect, the output or the action that the agent takes is highly dependent on the relative altitude in this region. But no matter the time to collision, it doesn't really change the action. So we can see we have a very low weight for time to collision. And so we could do this in a bunch of different areas of the state space and get this idea of like where each input feature is important to the action that the policy takes. Any questions on that? Yeah.
Is there a principal way to sample like what goes into training linear model? Like, you know how we spend a lot of time talking about falsification or finding important points. Do we want to like set our weighting exogenously to something we know would be nice? Or,
like in terms of like where to
sample,
to do this?
Sample it, how to weight the linear models.
Yeah, I feel like you just need like some domain knowledge of where you think where you don't understand and want to produce a linear model of to understand. Okay, and then as I mentioned, there's this trade-off between fidelity and interpretability. And so the better that our model fits, for example, the policy in this region, generally it has lower interpretability. So if we want to get a better fit, so like this straight line here doesn't really seem to fit this curved edge very well, we could add more features. So instead of just the state variables like h and time to collision, we could add like time to collision squared or like h times time to collision or whatever. But now if we look at these weights, we're like, okay, like h times time to collision has a higher weight than just h by itself, but it's like not super interpretable to us as to like what that actually means. So even though it fits it better, we kind of lose some of that interpretability. And in general, when you're doing these things, you need to make decisions that help you like balance these trade-offs. Okay. It's white now because I didn't have time to turn this into dark theme. So another example of an interpretable model is a decision tree. So we're back to our collision avoidance policy here. And we can now try to train a decision tree to approximate this policy. I'm not going to explain like how you train decision trees, but there's nice packages out there to do that for you. There's one in Julia called decisiontree.jl. Oh man, I thought I removed this. Okay, these are actually labeled backwards, so ignore them or reverse them in your mind. I fixed that in the book about an hour ago. Okay, so basically though, we've trained a decision tree to approximate this policy, and what this decision tree is showing is all the black nodes indicate a split on the relative altitude dimension, and then if we had any gray nodes, which we don't, they would indicate a split on the time to collision dimension. So basically we're saying, okay, to start at relative altitude of 0, if our current relative altitude is greater than 0, then we go over here, and we ask ourselves one more question, is our current relative altitude greater than 98? If so, then we're separated enough, and then we can be clear of conflict. If not, we're a little bit close together, we should tell the aircraft to climb. We should tell the aircraft to climb, and then that way we'll get more relative altitude. We could do the same thing over here. We'll say like, okay, we're less than 0. Are we far enough less than 0? Yes, then no advisory. Are we too close? Then we tell it to descend. Any questions on like what this decision tree means? Okay, so this is like very interpretable to us. Like, seems like the policy is like pretty sensible. Like, if it's above you, then we check how much above, and if it's far enough above, we do nothing, and if it's too close, then we tell it to climb. Like, this all seems reasonable, so this helps us interpret our policy. But of course, it's not exactly faithful to the true policy. So here's what this decision tree policy would look like. We kind of just created these layers here, basically. And again, we have kind of the same trade-off between the fidelity and the interpretability. So here, we can get a decision tree to represent a policy that looks much closer to our true policy, but then we have this big decision tree with lots of different branches that we would need to go down to try to understand what it's actually doing. Okay, so that's surrogate models. Now we'll talk about the last two very briefly, starting with counterfactuals. Okay, so with counterfactuals, I'm going to give you a little bit of behind the scenes into me making this lecture. So here's basically what happened. So I was going to be out of town this weekend, and I was kind of pushing up against the end of last week, and I was like, I really need to get this lecture done because I'm not going to have time to work on it on the weekend. And so Friday was supposed to be my day that I was like very productive on this lecture. But you may have noticed this like Band-Aid on my face, which basically I got bit by a bug, I think, and I woke up on Friday morning and like my whole right side of my face was like super swollen. I couldn't even like open my eye all the way, and I was like, this is not good. My husband looked at me and he was like, you need to go to urgent care. I FaceTimed my mom, she was like, you need to go to urgent care. I was like, all right. So I spent my Friday morning in urgent care. Turns out apparently it's fine and the swelling's going down, but I don't know. So I wasn't working on this lecture, basically. And then I was working on this lecture very late last night. And I have just found myself wondering that if I could go back in time and not get bit by this bug, would I be able to actually have time to explain counterfactuals to you? And the answer is maybe, but not today. Okay, maybe the people laughing harder got the deeper meaning of that joke, which is like that's a counterfactual itself. So basically a counterfactual is like when you go back in time and say like what would have happened if I did this, and so that could be a way to explain your methods. And if you're interested, you can check out section 11.5 of the book. But yeah, I really didn't have time to make slides on that. Okay, so that's counterfactuals. The last thing is failure mode characterization. So a lot of times we've maybe learned about different algorithms that we could use to find different failures of systems. So maybe we did falsification or we sampled from the failure distribution and we have all of these failures and we want to basically make sense of them. And so we can actually just use clustering algorithms to do this. So we'll basically create groupings of failure trajectories that are similar to one another, and sometimes that can give us some insight into what's going on or what these different failures mean. So I'm not going to go like super in detail on clustering algorithms, but like basically what you could use a very common one called k-means, which just kind of iteratively finds two nice distinct clusters or however many distinct clusters you want to try to find of your data. So here we're doing that on the pendulum, and you can see like over time, we eventually converge upon these two different clusters. And whenever you do this clustering, you need to pick what features you want to cluster based on. So here we're clustering all of our failure trajectories based on the average angle of the trajectory and the average angular velocity over the trajectory. And it turns out when we do that, we get these two really nice clusters. Nothing too crazy is going on here though, we just get a cluster where it falls over to the right and one cluster where it falls over to the left. But in general, when you have lots of failure modes and they're not so easy to interpret, this can be a nice, useful tool for you. And in general though, the results depend on the features that we use for clustering. So there we picked, kind of just hand-picked average theta and average omega. But we could just do it over the entire state vector. So we could just take, the whatever dimensional, like 100-dimensional state vector that we have and just cluster in that 100-dimensional region. And we still get something actually pretty interpretable. We get the same thing. We could also cluster over the action trajectories, so we can just take all the actions, stack them together, and cluster in that space. Or we could cluster over the disturbances. In this case, for the pendulum, clustering over the disturbances didn't result in something that was very interpretable to us. We just kind of get a big mix of trajectories there. That doesn't mean much. But if this is interesting to you, you should talk to because they recently did some really cool research where they were able to kind of create, look at a subspace of this by performing PCA and trying to understand clusters in the high-dimensional disturbance space. So potentially interesting avenues there, and you can talk to if you want to know more about it. Okay, and then lastly, another thing that's really cool that I'm not going to get super in detail on is that we can cluster based on temporal logic features. So like I said, everything you get out of this is really dependent on whatever features you throw into your clustering algorithm. But you can actually get really creative on the features that you do throw in there. So there's this thing called parametric signal temporal logic, which allows you to assign parameters to temporal logic formulas. And you can actually do your clustering in that particular parameter space. And so then your clusters will like correspond to different temporal logic formulas. And that would help you basically understand like, okay, these failures, for example, in this case, it's like these failures are failures that fell over before time, whatever. And these failures are failures that fell over after time, whatever. And so you can get kind of more interesting, more interpretable clusters by automatically doing it in the temporal logic parameter space. Cool, okay, so that's pretty much it for explainability techniques. So we talked about a whole bunch of different explainability techniques, talked about how maybe it's a little bit contentious. And in general, I just want you to keep in mind that there are just some things in this world that can't be explained.